let's look at tutorial 3 here, which is the LED flash code. And you'll notice right off the top here that I have a new title. Okay, most programs just actually mention the main as main, but I just put main LED flash to differentiate it from other ones, but you can just leave it as main if you like. Remember to fill in your author, your name, your date, a title, okay, and then the hardware descriptions as well. So if you have RB0 to RB9 connected to 10 red LEDs like I have, and maybe a button input, whatever that happens to be, make sure you fill that in, okay? The include files are the same. This delay right here, this constant, symbolic constants, are again used by the define directive, and they are named using all caps because that's how we name those constants. So if I wanted to name it, say, short delay, it's 2 words, and I have to separate it with a not a semicolon, but an underscore. So if you can see, having it together like that is just not easy to read. So that's how we separate it. That's how you should always do your constants. This 50 is going to represent the number of milliseconds. And so 50 milliseconds is quite small. This is 1250 milliseconds, which is a second and a quarter. Okay, and that's why I've named it short delay and long delay. All right, local function prototypes. Now these local function prototypes come from the delay.h header file. So if I go up to the top here and inside my delay header file, you'll see there's 2 functions. This first one, void init timer, which initializes the timer, so we can use that as part of the delay. And then I have this other one, void delay unsigned long milli, okay, which is taking milliseconds as a parameter. All right, so whether it happens to be 50 or 1250, and then it's using that to actually make the processor do nothing for that time, which is what a delay is all about. So I need this header right here, and I need this header here as part of my function header prototypes, which is why they're listed here and here. If you decide, which you will, I'm sure, when you're doing your robot in particular, to make functions, or if you just want to make functions at any point, at the bottom, you'll see you can make them below your main, then you will have to put your local function prototype here, which again is just that header with a semicolon. All right, global variables can be seen by every part of the program, and we have one here called unsigned int I. This is going to be used in the for loop, and it's unsigned, so we start at 0 and we can go all the way up to a 16-bit integer value. All right, here's our main function. So this is where the body of the code exists. We know we have our int main void, and so everything in between this opening and closing brace is part of that. I can actually click this little button there to expand it or contract it. So it's kind of a neat little function. If you have lots of functions and you don't want to look at them expanded like that, you can simply click it and it will shrink it. This first line of code, init timer, we have to initialize that timer to use the delay function. That has to be part of main. Even though it is in our header file, we have to actually use it. We have to call upon that function so that it initializes that delay timer. The next code here, you've probably seen this from last year. We need to teach all of port B to be outputs. Okay, so it's really important that we do that. When we're using ports, they need to be either inputs or outputs, but in this case, they're all going to be outputs. So I'm going to set that to 0. Now, I could, if I wanted to, let's say, set it to be all inputs. Well, if I wanted them to all be inputs, and I've got 16 bits, remember, or 16 ports, then I could use hex to do that. So I could do 0x FFFF. That would mean that they were all ones, which means they would be all inputs. Okay, so that's an easy way to use hex. But I'm just going to keep it as 0. That means it writes 0 to all the bits in all those ports. Initialize all of port B. Lat B equals 0. Okay, so I'm going to initialize all of those to be outputs, or sorry, all those to be 0. So that's the lat B port, which is the register I use to write to ports. So all of my LEDs, if I want to turn off or on an LED, I control that through lat B. So the difference here is that TRISP is teaching to be an input or an output. Lat B is actually writing to that port. And if you want to read from it, we'll see later, we use port A or port B. We have for loops, And contained inside this while loop, we have 3 loops. So this while loop is our endless loop, which has a condition of 1, which is always true. And you can see this opening and closing brace, which is our compound statement. So here's our compound statement. Here's a great example of a compound statement which contains other compound statements. Okay, and in this compound statement, this one has a for loop, okay, which has a compound statement, as do the 2 below it. Now the conditions are slightly different. This one I want to flash this least significant bit, LED, 3 times. And here I want to do this 6 times. So you can see the condition has changed from I is less than 3 to I is less than 6, and I'm incrementing it up by 1. Okay, this one is only actually doing it twice. Okay, and those for loops have those 3 expressions, as we've shown in the video series on loops. Now this is curious here. I can write to the entire register, as I've done here, which is lat b equals 0, which writes to every single bit, so all 16 bits of that register. Or I can, if I want to in this case, control each individual port or each individual bit. So what that means is I'm going to have to use the bits modifier here. So rather than saying lat b equals 0, I'm going to have to say lat b bits equals dot lat b0 is equal to 1, which is sending a 1 or turning on that lat b. The reason why I'm showing you this is because I wanted to highlight something, and the reason why I had given you these sheets on the SFRs, which are the special function registers in the PIC. Okay, I had actually given you these as part of a handout. And if you scroll down on your sheets, you will come to one of the most important ones, which lists all the registers. Okay, and let me show you this one here, which is the port A and port B register maps. Again, you can see it starts at bit 15 down here and goes to bit 0. So there's no bit 16 because you have to count 0. And again, if you let's look at register port B for a sec and expand that a bit. You can see that tris B, okay, is all of these 16. So if I say tris B is equal to 0, as I did in that one line of code, I'm writing a 0 for every single one of these registers. So every single one of these ports is going to be an output. If I wanted only one of them, let's say the last one to be an output, then I would just put maybe tris B bits dot tris B0 equals 0. Because maybe I want this to be an output and I want this to be an input. If I wanted this to be an input, I would write tris b bits dot tris b1 equals to 1. And I'm teaching this port to be an input. Now the lat b, okay, let's say I want to flash one of my LEDs. Let's go back to this code here. I want to flash the least significant bit. So that's lat B0. Well, how do I know it's called lat B0? Well, because here's lat B, and look at the name. It goes from lat B0 all the way to lat B15. Okay, so if I want this to flash, I have to say lat B bits dot lat B0 equals to 1. And then if I want it to write a 0 or turn that LED off, I simply go lat b bits dot lat b0 equals to 0. I need a delay in between so that I can see that turning off and on. Okay. Same thing down here. I'll just show you. I'll skip down to here. Lat b equals 0x ff. Why do I do that? Well, the ff is a nice thing to have that writes to all of these 4 bits, because f is 1111, right? So it's going to turn these 4 on, then it's going to turn these 4 on. So there's f there, and there's f here. 1111, 1111. So that's a nice little way of describing or showcasing how hex is a really easy and useful language when writing. And notice that I'm not saying bits, I'm writing to the whole entire port here. Okay. This example in the middle, I wanted to save that for last, uses a bitwise operator called the XOR bitwise operator. Now, what's interesting about this one is that I start with lat B7, okay, being equal to 0 because I've initialized the port to be 0 from this command here. Well, if you think about it, what happens when you XOR anything with a 1? Well, if this is 0, because that's what it is, I've got a 0 and I am XORing with a 1. What's a 0 XOR 1? Well, that results in a 1. So it turns on this particular bit, and which is bit 7 of lat B, so RB7. Then it comes back around. And lat B now is 1. Well, what if I XOR a 1 and a 1? Well, it becomes a 0. So it turns off. And then the whole process repeats itself over and over again. So the XOR bitwise operator is very useful for toggling. So from going from a 0 to a 1 and back to a 0 without having too much effort. And you can see that's a nice slick piece of code there. Okay, so that concludes the explanation of tutorial 3. You can mess around with that, and I've got some challenges for you to complete after you're finished writing this code.